Hi, and welcome to this last video in this section on equations of motion. And what we're going to be dealing with in this video is still SUVAT stuff, but in terms of things being thrown up in the air or dropping out of the air. So we're talking about vertical motion. So we've been through different definitions. We've been through time graphs, velocity, time. We've done SUVAT equations. This last section here is an application of simply SUVAT equations, as we'll see in a second. So here we go. Right, so the key idea here is like if we've got an object falling, then they've got a constant acceleration of 9.8 meters per second, which is value g. Now that g is indicates gravity, not grams. Please don't get confused. The other thing to mention is the physicists amongst us, you'll be familiar with g, but in physics they use a value of 9.81. In maths we're using 9.8. All right, so it doesn't matter how big this object is, the mass doesn't matter at all. Say if something's falling due to gravity, it will be accelerating at a rate of 9.8 meters per second. And we've got an assumption that air resistance is so small that it can be ignored, which allows us to work with constant acceleration, which is what we need for SUVAT equations. And that is primarily because it just keeps the models much more simple to deal with. And because acceleration is constant, that is the key thing that we need for SUVAT. So basically what we're doing is going to be applying the SUVAT equations. So here we go. The ball is dropped from a point 10 meters above the ground. How fast is it moving? Where is it after 4/7 of a second? So it's a SUVAT thing, so SUVAT. Now, key thing here, of course, is that we're told it's dropped from 10 meters above the ground, but we don't know the displacement. We don't know how far it's traveling. That's the where part, so we haven't got that one at the moment. I'm going to focus on the how fast is it moving, so to begin with I don't know displacement. U is going to be 0, implicit in the question, because it was it was at rest when it was dropped. V, that's the thing we're trying to find. A, we know is 9.8. And at this point, because the motion is downwards, we'll say that okay, if we just assign downwards as being our positive direction, that allows us to use acceleration being 9.8. And we've got T, which is 4/7 of a second. So we're going to want V, we want the one that doesn't involve S, so we're on V equals U plus AT. Plug the values in, and V equals 5.6 meters per second. And that's kind of, you can see there why we use 9.8 rather than 9.81, because you tend to find a lot of 7ths and 14ths being used in these questions, because 98 is a multiple of 7, and it just means that numbers are simple to deal with at the end of it. So there we go, V equals 5.6 meters per second. The second part of the question, where is it after 4/7 of a second? So this is now where we want displacement. And so I'm going to use that one again, because I actually know all of them. It doesn't really matter what I'm going to use, but we'll use the 1/3 displacement. And it's easy to use because U is 0, so that gets rid of that bit. So we've just got half times by 9.8 times by T squared, 4/7 squared. And so S is 1.6. So you'd have thought we're at the end of it, but we just need to be a little bit careful here, because where is it after 4/7 of a second? It's travelled 1.6 meters, but if it started 10 meters above the ground and it's travelled 1.6 meters, that means it's now 8.4 meters above the ground. Okay, on we go. So in that last example, we just dropped a ball from a height. Let's consider now what happens if we've thrown a ball or an object up in the air. Now, if it's being thrown upwards, we're giving it an initial velocity. So imagine I'm throwing a ball up there. When it leaves my hand, it's already got a velocity, so U won't be 0. And once it's in the air, the only force acting on it is gravity. There's nothing else happening. So therefore, it's acting under the force of gravity, which is an acceleration of 9.8 meters per second. What I'm going to be doing is say, well, if I'm throwing this ball upwards, and so in this case I'm going to take upwards as being my positive direction, it's slowing down as it goes up. So what I'm going to do is say we've got deceleration. So I'm going to say acceleration is minus 9.8 meters per second. The other thing to realise is once it gets to the top of its flight, how high it's gone, it then starts moving down again, and now it's accelerating at 9.8 meters per second. So what we've got is constant acceleration throughout this entire thing. So it doesn't matter if it's moving up or down, it's still got this value that is 9.8 meters per second. So here we go. The ball is thrown vertically upwards, rises to a height of 10 meters. Find the speed with which the ball is thrown and its velocity when it's risen 7.5 meters. So we're going to take those two bits in two parts. I'm going to deal with the speed bit versus the speed with which it was thrown, which is u. So it rises to a height of 10 meters. The speed at which it was thrown, that's the thing we're trying to find. Now, when displacement is 10, it's at the top of its flight, and it's instantaneously coming to rest. So what imagine the ball is going up, it's slowing down, it's slowing down, it's slowing down, then it gets to the top of its flight. For a fraction of a millionth of a second, it has got a velocity of 0, and then it starts moving downwards. So basically the key idea here is we're saying that the velocity at its maximum height is instantaneously at rest, so velocity is 0. Right, we've got acceleration, minus 9.8. I'm modelling this as upwards being the positive direction, so acceleration is downwards, so therefore I've got a equals minus 9.8, and t is the thing we don't know. So we've got to pick an equation. It's the one that doesn't involve t, so that's v squared equals u squared plus 2as. Chuck in my values and do a bit of solving, and there we go. We can see that it was initially, when the ball was thrown upwards, it was moving at a speed of 14 meters per second. Find its velocity when it's risen 7.5 meters. So v squared equals u squared plus 2as. At this point, we're changing it slightly, so kind of s is no longer 10, because we want to know what's going on when s is 7.5, so I'm just switching that value there. So that's why I put that value in like that. So we've got v equals 7 meters per second. Now, before we move on, it might be that the sharp ones amongst you out there watch this video might think, well, hang on a second. If I'm doing a square root, I'm going to get a positive value, and I'm also going to get a negative value. Come on, what's happened to the negative value? Well, as it turns out, that is a relevant value. In this particular question, we're asking for its velocity when the ball has risen to that height there. The negative value will be the speed the ball, the velocity the ball is travelling at when it comes back down, and it's 7.5 meters off the ground on its way back down to the ground. At that point, it will be travelling at minus 7 meters per second, minus because the ball is now moving downwards. So if you clock that one, well played. That's saying, and again, it is something to be aware of when you're working with these kind of questions. Okay, moving onwards. What we're going to do now is just think a little bit about what happens when the ball's coming back down, which is what I was alluding to on the previous slide. So because acceleration is constant throughout this, it's minus 9.8 meters per second. So as it goes up, it's decelerating at minus 9 meters per second, and then when it comes back down, it's still got an acceleration of 9.8 meters per second. So we can use the same set of equations throughout the motion. And what I'm going to do is just think about that previous example. I'm just going to consider that one there, which is displacement, and we had a value of u was 14, a is minus 9.8, so that gives us that equation there. So that's our displacement equation, and if I plot that on a displacement time graph, what we get is that which is a nice looking quadratic. And so what you can see clearly there is a maximum height, which is happening at 10 meters. And you can see that it's quadratic, so it's symmetrical, so what goes up must come down and do it in the same way. And let's now have a little think about what's going on with the question. So let's ask the question, after how long is the ball 6 meters from the ground? So there we go, there it is on our graph. So let's just plug in a value of 6, do some solving, and we get two values. So it's 6 meters from the ground on the way up after just over half a second, and then on the way back down after approximately 2 1/3 seconds. For how long is the ball in the air? So we need to find essentially that value there, and to do that, what do we know at that point there? Well, we know that displacement is 0. So we can just plot that equal to 0, do some factorising. Again, how you choose to factorise that is up to you. You could just take out the t if you wanted, and we end up with t equals 0, and t is 20/7. Okay, the t equals 0 clearly is going to come from the fact that at the start of this, displacement is 0 when t is 0. So that's our default setting. Right, you'll notice as well that the total time it took was 20/7. If you remember back to the previous slide, so we reached the maximum height when t was 10/7. i.e. because of the symmetry, that value there, 10/7, is exactly half the total length of the flight of the ball. So again, if you wanted to find the point at which you got a maximum, you could go for half the total distance, or you just use that factor however you want to use it. So to find the velocity of the ball when it hits the ground, well, when it hits the ground, v equals u plus at. When t is 20 over 7, we've got v equals 14 minus 9.8 times 20 over 7, and v equals minus 14 meters per second. And again, thinking about the symmetry of the whole thing, we said the ball was initially projected at 14 meters per second upwards, and when it hits the ground, it's travelling at exactly the same speed, but obviously its velocity is different because it's now travelling in the opposite direction. So those are the 2 points that we just made.